Here's another example of potential energy. If we have a spring, it has a natural or rest length x0. If we try and compress it, it'll push back on us. If we try and extend it, it'll pull back. That means the restoring force is in the opposite direction to the length change. This could in general be a horrible mess, but it turns out that it's just a proportionality in all the cases we're going to care about. So we could write this as F spring is negative k times x minus x0, where x0 is rest length. We could also write this as negative k delta x. K is the spring constant, and it depends on how the spring is made, what it's made of. The units have to be newtons per meter, and K may only be a few newtons per meter for something like the spring in a ballpoint pen, but it could be over 100,000 for a spring in your car's suspension. This F being proportional to Kx is known as Hooke's law, and it actually works for many, many things that we wouldn't consider to be springs, like a steel beam or a wooden beam for that matter, over at least some region of motion, and this is the elastic region. Beyond that, you can have a sudden, huge increase in length without much of an increase in force. This is the plastic region, and the spring doesn't come back from this. If you want a cheap example, you can try this with a ballpoint pen spring. You can stretch it, and then all of a sudden, you'll feel it move a lot when you haven't pulled much harder, and it won't come back to its rest length. Measuring K is easy. We can just hang a weight from the spring. It'll stretch down to a new length, x, and we know that K times that length change has to equal mg, since those are the only forces involved. One other thing we should notice, it's sloppy, but instead of writing F is negative K times x minus x0 or negative K delta x, people very commonly just write F spring is negative Kx, but they assume everybody understands that what you mean is really delta x instead of x. If we want to find the work done to extend the spring, we can use this work energy theorem again, and we put in our F as Kx. We don't have a negative sign because this is the work we're doing in opposition to the spring. We pull the spring to the right, it extends to the right. The spring's force is to the left, but ours is to the right. When we do this, this is a very simple integral. We get 1/2 k delta x squared, or again, as I said, the way people usually write it, 1/2 kx squared. This is the work done, and this is also the energy stored in a compressed string or a stretched spring, and it's known as spring potential energy. This only exists because the spring force is conservative. So you could take your spring and move it way out and back, way in, back and forth, but all that really matters is where did you start and where do you finally end up. It's path independent. This is one more kind of energy, and we can add it to the list of energies that we know. So for an example of this, we can imagine that instead of motors and chains, we're going to build an amusement park with a roller coaster where you're fired out of a spring like a pinball, and then you climb the hill and go down. And we'll put in some numbers. We'll say the car's mass is 750 kilograms, the spring constant is 1,000,000 newtons per meter, and the hill is 80 meters tall, which is pretty ridiculously tall. If there's no friction and no air resistance, how much do we have to compress the spring? So we say before launch, let's call the total energy EI for initial. It's all the energies that we know about. 1/2 KI squared plus MGHI plus 1/2 MVI squared. Now if we're smart, we notice that the cart starts out at the lowest height, so we'll make HI 0. That gets rid of that piece. Also, since the cart is not moving before we fire the spring, VI is 0. So our initial energy is just 1/2 KXI squared. Then we can go to the top. This is what we're trying to get to. We again list all the kinds of energy we know. The spring is here, but it's already extended and gone back to its rest length. There's no spring at the top, so this part disappears. The velocity, technically it has to have a little bit of velocity or it'll get stuck on the hill, but if you've ridden a roller coaster, you know when you're coming over the very top of the main hill, they have you going very, very slow to try and scare you. So we can say VT is pretty close to 0. So what that gives us is E at the top is MGH. Because energy is conserved, EI has to equal ET. We can set these two equal to each other and solve for XI, and we see that we really only have to compress the spring a little more than 1 meter to do this. What if we want to know how fast the car is going after it leaves the spring, but before it starts climbing the hill? So right here, for example. Then we can say that we know energy at that point will be 1 half ks squared plus mghs plus 1 half mvs squared. Now the spring is already fired, so that disappears. We're still on flat ground, so hs disappears, and we just have this. And the reason we do this is we know that this energy at this point, S, is equal to the energy it had in the beginning or the energy at the top. So you can use either this or this to get the answer, and you'll get the same thing. So we could write, if we use the kinetic energy is equal to the potential energy at the top, we get Vs is square root of 2gh. On the other hand, if we use kinetic energy is equal to potential that was stored in the spring, we get Vs is xi times square root of k over m. Either way, we get 39.6 meters per second. We could mix these and say, what about while the spring is in the process of firing, it hasn't completely launched the car yet. What if its compression is down to 0.75 meters from 1.08? How fast is the car moving at this point? We can call this point B, and we have E initial is all the same stuff we mentioned before, but again, for the same reasons, the only part that survives is the spring. We start with 588,000 joules. At point B, we have all the same energies, and we have two contributions because the spring still has some compression to it, and the cart has gathered some speed. We're still on flat ground though, so we don't have an MGH. XB is 0.75 meters, so we plug this in, we do some math, and we see that at that point the cart is moving at 28.6 meters per second. Notice that this principle is conservation of energy, not conservation of kinetic energy or gravitational PE or spring PE. Those things themselves are not separately conserved, as you can tell by throwing a rock in the air. It starts off with KE, that disappears when it reaches the top, and it becomes all gravitational PE. That disappears as it falls back down and turns into KE again. So separately they're not conserved, but the sum will be. All the examples we've used so far in this work energy theorem are using conservative forces, but that's not the only kind. What if we kick a block across the floor so it has kinetic energy and it slides to a stop? We know the kinetic energy has disappeared, but where did it go? There is no potential energy that's appeared. Work had to be done to get rid of that kinetic energy, and that work is done by friction. So, using the work energy theorem, we plug in the value Fk, we know we're talking about kinetic friction if we have a displacement, times dx times cosine theta. The big deal here is theta is 180 for kinetic friction every time because it always opposes the motion. Since kinetic friction only depends on normal force of mu k, it doesn't have a distance dependence, so this integral is trivial, we just get a distance out of it. W is negative Fk times d, where d is the distance traveled. This is not path independent, and the reason is, in the examples with the spring and gravity, which were path independent, there are times when you move that those things help you. If you're moving down, gravity helps you. If you're bringing a spring back towards its uncompressed position, it helps you. You get energy back. Friction doesn't work like that. The force always changes direction to oppose your motion. So if you imagine moving a refrigerator from one side of the room to another one, sliding it along the floor, these two paths are going to require a very different amount of work. If you think about this in the financial sense, this work, which is called non-conservative work, kind of like a service charge. Your balance drops, but you didn't get anything you really wanted, like water or rent, out of it. So really, we could write a new formula instead of E initial as E final. We have E initial plus non-conservative work is E final, where this non-conservative work is negative. In financial terms, we could say we started with $100, the bank took 10, and your final balance is 90. Now, that frictional work does generate heat, you probably know from experience, and when we get closer to the end of the course, we'll see how we can use that energy that becomes heat to figure out the temperature increase of a block